Hopefully this was an easy question. I hope you realize that the current through A has to be the same as the current through B, because what we're talking about here is a flow of electrons. And if the current at A isn't equal to the current through B, then either electrons have been created or destroyed. However, it is a persistent misconception that people have that the current at B would be lower. People seem to think somehow that the electrons get used up somehow in the light bulb. But remember, those electrons are indestructible. They can't get used up. They do have less potential energy when they come out the other side of the light bulb. If they were to disappear, it would be every bit as strange as the situation of Psy mysteriously disappearing as he goes around the corner. Well, it's story time. Here is a story about two lands, the mire of debt and the field of credit, which are separated by the great social chasm. And the people in the mire of debt are all in debt. There are 20 people living there, and each of them has $100 of debt as their net worth. And so the national wealth of the mire of debt is negative $2,000. Meanwhile, in the field of credit, people have money. There are 12 people there, and each of them has $100. And so the net national wealth of the field of credit is $1,200. But one day, the people in the mire of debt decided they didn't want to live in the mire of debt anymore. They wanted to be in the field of credit, and so they built a bridge. And 8 of them walked across the great social chasm into the field of credit. Note, though, that as they went, they took their debt with them. They can't really escape their debt. And so, as the 8 debtors crossed the bridge, they brought their $800 of debt with them. And so now the mire of debt only had a total debt of negative $1,200, but the field of credit had its $1,200 and the $800 of debt, and so its new national wealth was only $400. Well, notice that it is exactly as if $800 had traveled back across the bridge from the field of credit to the mire of debt. In terms of the national wealths of the mire of debt and the field of credit, that flow of cash in the opposite direction to the flow of people would have had exactly the same effect. So, when particles move carrying a negative quantity, the flow of the quantity that they're carrying is in the opposite direction to the direction that the particles are going. Up until now, as I've talked about motion of charges in a circuit, I've been talking about electron current. But when we actually measure current, that's not what we measure. Note that the flow of electrons will have the same effect on charge distributions as a flow of positive charge in the opposite direction. And that's what we actually measure and call the charge current, which means it must go in the opposite direction to the electron current. This is often called conventional current, or it just gets called current. That's what I'm going to do. Whenever I just say current, I mean charge current, and that's a flow of positive charge, which means if we're talking about flow of charge in a wire, which is electrons, then the charge current is in the opposite direction to the direction that the particles are actually moving. Now we're going to expand on the ski hill analogy that we saw before to incorporate current into the analogy. So we've already seen that height on the hill is in some sense just like potential in a circuit. And we can expand the analogy around that to say that the ski lift is the power source and the slopes that the skiers go down are the load in the circuit. But now let's add current in. Note that skiers are conserved. Skiers are not being created or destroyed on the hill, unless perhaps there's a bear on the hill somewhere eating them. But we're going to talk about circuits that have no bears in them. So skiers are conserved just like charge. And so the traffic on the hill, which you could think of as a number of skiers per hour passing any point on the hill, is in some sense just like current, because it's a flow, a motion of a conserved quantity. With this expansion to the ski hill analogy, we can now talk about the other big law that always holds in circuits. Let's think about junctions. So when a trail on a hill splits, like it has in this orange circled area here, then we know that skiers are going to arrive at this junction, and they're going to leave the junction by multiple trails. But what has to be true is that the number leaving per unit time must always equal the number arriving per unit time, because skiers will not simply pile up at the junction, and certainly skiers are not being created at the junction. And so, for example, if there are 50 skiers per hour arriving at the junction, and we know that 30 skiers per hour leave via one trail, then without doing any counting at all, we know that there must be 20 skiers per hour leaving by the other branch. When trails on a hill join, as they do at this purple circled place, then we have the same sort of thing going on. The number arriving via all branches coming in must equal the number going out. And of course, this would also apply to more complicated places where trails cross, and now the sum of the skiers per hour coming in by all branches will equal the sum of those going out by all branches. Well, we were able to argue that with skiers because skiers are conserved, and charge is conserved too. And so we must have a similar rule for junctions in circuits. So in this battery and trio of light bulbs, we might have, suppose, 30 millicoulombs per second coming out of the positive terminal of the battery. Remember, that's the charge current. Really what's happening is that electrons are going into the positive terminal of the battery. Those 30 millicoulombs per second arrive at bulb A, and we already know that all 30 millicoulombs per second must leave battery A. Now they get to the junction, and if we know, for example, that 10 millicoulombs per second go from the junction into bulb B, then there must be 20 millicoulombs per second heading down to bulb C. And both of those currents must be the same on the other sides of bulbs B and C, where they rejoin at the other junction, so that 30 millicoulombs per second again arrive at the negative terminal of the battery. Now remember that what's actually going on is that electrons are going in the opposite direction to what I've drawn here. But in fact, it's very hard to do an experiment where you can tell the difference between positive charge moving one way and negative charge moving the other way. The other reason we talk about charge current instead of electron current is that it's more universal. Because whereas in wires what's moving is always electrons, in other things the charge may be carried by different charge carriers. So, for example, if the battery is a car battery, then we know that in the wires we have the electrons going in the direction I've shown, leaving the negative terminal of the battery and arriving at the positive terminal of the battery. But the charge carriers inside a car battery turn out to be hydrogen plus ions. And so those must be going in the same direction as the charge current, because those are positive particles. And so they are leaving the negative terminal and arriving at the positive terminal, going inside the battery. Notice that the charge current is in the same direction the whole way around. The current through the battery, by which I mean the charge current, must be the same 30 millicoulombs per second, and it must be going the same way around the circuit as the current is everywhere else in the circuit, even though it's being carried by different particles moving in the opposite direction. This idea that I've just used to talk about currents in and out of any junction being equal is referred to as Kirchhoff's junction law. And so one way of writing it is that the sum of all of the currents into any junction must equal the sum of all the currents out. As I'll argue in a later lecture, that's not always the most convenient way to write it, but it is a nice, easy way of thinking about it.